Now I will talk about Rossby's planetary waves. I don't want to call them Rossby waves because I feel there is a lot of misunderstanding about Rossby waves. And Rossby waves only were called that after Rossby's death. In his own lifetime, he and others talked about planetary waves. And one reason why I don't like anymore the notion of Rossby waves is because of a conversation I had 20 years ago at the European Centre over a lunch. A scientist asked me about the weather the coming weekend, and I said, well, it will be fine. Why? Well, I said, there's a big Rossby wave is coming in. Then the scientist said, but can you see a Rossby wave? And he was a very theoretical man. So I understood that he had just seen Rossby waves in his equations. And he also had a notion that could only see Rossby waves by some clever spectral analysis. So I was a bit, did not know what to answer, except that, well, Rossby himself must have seen something in the 1930s when he discovered these waves. And Carl Gustaf Rossby was a Swedish meteorologist who moved to America in 1926, wanted to promote dynamic meteorology but also operational weather forecasting, and he became one of the great men in meteorology. So here are his main dates until the Second World War. He was both theoretically involved in the Bjerknes group in Bergen in Norway. He was a weather forecaster, and he worked on the geostrophic adjustment problem when he actually discovered his waves. And the reason why he did that is quite interesting because, as I said, he was mainly interested in the geostrophic adjustment problem, but reality from outside came in. And in the 1930s there were drought years, problems with the harvest. It was a long period of no rain and heat, and this together with the depression caused a lot of people having really bad. So Rossby and his team had a request from the government to produce methods for 5-day forecasting that would help the farmers. And the Rossby team, after a couple of years, made a discovery that above the normal surface weather, the one we experience daily, with low pressure and high pressure systems, higher up in the atmosphere there were also waves or cyclones or anticyclones, but they were much bigger and more slowly moving, and they seemed to be steering the small-scale weather at the surface. So here is an example from 1940 where the Rossby team had analyzed the flow pattern, I think 3 or 4 or 5 kilometers up in the atmosphere. It was before there were many radiosondes, so a lot of it had been used balloons or pilot balloons or other ways to trace the motion in the higher atmosphere. So here you can see, here is North America, and you have one major upper low pressure system or trough, but you also have a trough west of America over the Pacific, and one cyclone somewhere over the Atlantic. And these are what they call planetary waves. Planetary meant that it was big waves. And he found an equation that roughly described the phase velocity, the phase speed, c. The phase speed c was a sum of two conflicting motions. One was the west wind, transporting things from the west to the east. But then there was a minus term, and it was proportional to the square of the size of the wave divided by 4p squared, and a term beta. And beta is the variation of the Coriolis parameter, the Coriolis force. The Coriolis force is proportional to the sine of latitude. And the derivate, the north-south, becomes, of course, proportional to the cosine of the latitude. So beta is 0 at the poles and has its maximum value at the equator. And it means that for long waves, this term could be larger than the u, and small waves, it was smaller, so small waves would move eastward and long waves move westward, and then for some values it could even be stationary when these two terms compensated each other. And this wave equation was used in practical forecasting. So for, let's say, stationary waves where c is 0, you could calculate the typical wavelength. And then you could compare this typical wavelength for a stationary wave under these current west wind conditions with the existing waves. And then if there was a if the current wavelength was the same as the stationary, you could assume that things would not change. But if they were different, you could assume that the waves would move either to the east or to the west, depending on if the current wavelength was larger or smaller than the theoretical stationary wave. So this was the first way to mathematically make forecast, and it was, I know because it was used when I was young and I came into meteorology, it was used to make 5-day forecast at the Met Service I served in Stockholm. So his equation was very important for the development of meteorology. And doing so in the Western Pacific, in the Western Atlantic, we have strong contrast in the sea surface temperature. They are also close to mountains further upstream. And this leads to that the troughs, the low pressure systems, in this part and in this part tend to be locked or semi-locked to the surface. So they are less inclined to change, whereas troughs between them are more easily moved. So you could also use this notion that, assuming that these were more or less in the same place, if the wind was increasing or decreasing, you could infer that, for example, for increasing westerly winds, there would be less waves. Some waves would disappear. If the west wind was weakening, more waves might appear between these anchor troughs. So it was the first step towards a mathematically derived weather forecast. And this planetary wave approach was also combined with isentropic analysis, and analysis of surfaces for constant potential temperature. So, and it led to quite wonderful, a bit three-dimensional images of the weather patterns. So already before America entered the Second World War, it was possible to issue useful 5-day forecast to the American farmers. And of course this also has a great importance then during the Second World War. But as in science, there are a lot of mistakes, and when Rossby published his result in 1939, he wanted to explain in the same way as I do, intuitively, what is going on. And then he made the mistake of confusing the curvature, because his explanation depended on the interplay of curvature and of the latitude with the larger or smaller Coriolis force. But he forgot that the curvature here is the curvature of streamlines and not curvature of the trajectories. So he, when the paper was published, he discovered his mistake and published a new paper in 1940, where he used trajectories and also potential vorticity. But very few people have read this paper. So in many textbooks you can still find explanations of Rossby's waves according to his first misleading derivation. Now, to simplify what he did in 1914, it's important to keep in mind two things. One is the difference between streamlines and trajectories, and the other one is that a trajectory, what that is central in his derivation, is a trajectory for a parcel that conserves its absolute velocity, its absolute vorticity. And the absolute vorticity is eta. It is the sum of the relative vorticity and the Coriolis parameter. And under certain conditions, in this case there is no divergence in the atmosphere, and that applies to the level Rossby was interested in, 5-6 kilometers height. Then you can assume that this is constant. And then you can map the trajectory of an air parcel for which this is true. When there is low relative vorticity, or negative because it's anticyclonic, then you have also high latitude, so they end up constant, and vice versa for lower latitudes. And unfortunately, what you sometimes see in the textbooks or on the web is that this curved trajectory is a Rossby wave. It's not a Rossby wave because a wave is defined according to its streamlines. And this is a trajectory moving through a planetary wave, or what some people like to call Rossby waves. So the relation between streamlines and trajectories is the second important thing to keep in mind. And here is the streamlines for a wave moving progressively eastward. And the trajectories for individual elements of mass or air in this will, if they move, and as they do in the atmosphere, they move faster than the patterns themselves. They will actually have larger amplitudes and longer wavelengths. So this is typical trajectories for streamlines moving eastward. And then for a pressure pattern of streamlines moving westward, as they can do in the Rossby scenario, then the wavelengths are shorter and the amplitudes smaller. So, but now keep that in mind. Here we have now this trajectory of an individual air parcel conserving absolute vorticity. And in the background with dashed, we have two streamline systems which actually both satisfy motion in these streamlines, satisfy the trajectory under first the condition that the small waves, these streamlines moving eastward, will have trajectories along this line. On the other hand, this very long or planetary wave streamlines, if they move westward, they will also lead to trajectories having this shape. So it means that this is how Rossby motivates that short progressive waves in its equation move eastward and long waves move westward. When this, after the war, there was some confusion about Rossby's derivation, because it was based on what is called barotropic ideas. It means that there are no thermal contrast. And in particular in Britain, people said that how can you say this, because the atmosphere is not barotropic, it's baroclinic. You have thermal contrast, warm and cold air mass contrast. And Rossby's answer was that yes, the atmosphere is baroclinic, has thermal contrast, but its motion in this level of no divergence can be kinematically described according to my barotropic derivations. So again, it's an example where it's important to keep the mathematics and the physics slightly on different sides. What is mathematically is not necessarily physically. Then we come to this beta effect. which I mentioned, the beta term, the north-south variation of the Coriolis parameter. And can that be understood? Yes, in my view it can. Here is now the inertia circle, which I have talked about previously. The motion of an air parcel or water parcel only affected by the Coriolis force. And it goes into a circle, I've been saying. Now that is, so now we come to the beta effect, which I have mentioned earlier in relation to Rossby's wave equation. It was a derivative of the Coriolis parameter in north-south direction. But can we understand what it actually means? And let's return to the inertia circle. It's not actually an exact circle, because the Coriolis parameter varies, as I said, with latitude. It means that the curvature of the inertial circles also vary with latitudes. So for one and the same inertial circles, there is a different radius of curvature in the northern side compared to the southern side. So here we have a shorter radius, and here we have a longer radius, and it means that the circle does not close. It opens up slightly to the west, not as much as I had done here for clarity, but still it doesn't open up, it doesn't close, it opens up to the west. And as a consequence, we have a slow and small transport of mass from east to west. So it's another example of the counterintuitive behavior of the Coriolis effect. It first of all constrains the motion of the air and the water, but then it also slightly moves air and water to the west. And this might help us to get a feeling for the Gulf Stream. A mystery for long times for meteorologists and oceanographers was that the Gulf Stream, to a large degree but not totally, driven by the winds. Why was it not symmetrical as the driving winds? The driving winds is the Azoric High. So here I have America to the west and Europe and Africa to the east, and the Atlantic with a subtropical high pressure system, and the wind is moving clockwise around it. So why is not the Gulf Stream more or less parallel? And we can understand that by coming back to the knowledge that winds over ocean tend to put the ocean circulation into inertia circles, or at least part of the motion is in inertia circle. And then adding on that this tendency to drift the water to the west because of the beta effect leads to that water is accumulated on the western side of the Atlantic and less on the eastern side. And if it hadn't been for the continents of America, of course, the whole thing would have moved out in the Pacific. But now America is there and as a barrier to this water transport. So now what we have is, in the same way as a Azoric High is an air mountain with most of the air in the center of the high pressure. Now this circulation will create a water mountain, and which is displaced or to the west. So most of the water, the maximum water, is displaced west of the Azoric High. And since there is now a steep gradient in the western part and a less weaker gradient to the east. And since air motion is governed by the catastrophic balance, so is water motion. So we will also here have a circulation more or less along the catastrophic relationship, strong in the northern part, weaker in the eastern, rather strong in the southern part, but strongest in the western part, just outside the American east coast. And this is where we have the Gulf Stream. And then finally, when I'm talking about the Gulf Stream, you might have heard about the Zaragoza Sea, where a lot of debris, both human debris and natural debris, tends to concentrate. And that is again partly an effect of the Coriolis effect, because when this debris is floating around in the Gulf Stream, in the ocean circulation. It's also deflected to the right, so it means that all the debris is accumulated and kept together by the Coriolis effect. Thank you very much.